So I couldn't get the printer to print on Friday. This was a little quiz or little thing I put on this TV screen. So let's review for the test tomorrow. So what region is W? Liquid. What is X? So liquid is going to be in the middle. Well, why? So again, draw an imaginary line somewhere that goes through all three regions. Solid is going to be at the lowest temperature, liquid in the middle, gas at the end. What is the normal melting point? Remember, normal means at 1 atmosphere. So what is the normal melting point? About 10 degrees Celsius. What about the normal boiling point? 40 is a good number. What is the letter Z referring to? That'd be the triple point. That's the point in which both solid, liquid, and gas meet up. If you increase the pressure from 0.5 atmospheres to 1.5 atmospheres, what happens to the melting point? It would be, so the melting point increases. So this is the melting point. Melting point isn't constant, it's based on pressure. But as we go from 0.5 up to 1.5, the temperature fluctuates somewhere around 10 or more like 8, so between 8 and 15 degrees. So it changes. What is the pressure and temperature in which all three phases coexist? So when do all three phases coexist? So 0.5 atmospheres. If we draw a line straight up here, it's not on the 10. So 8 to 9 degrees Celsius. A little less. What is the melting point at 0.5? 8 or 9? If the pressure is 10 degrees Celsius and is increased from 0.5 to 1.5, would the substance freeze or melt? So we go from this point right here up to this point right here. It's about a liquid, and it'll go into a solid, so it would freeze. What happens to the boiling point of water at lower atmospheric pressure? How does this affect cooking times? So what happens to the boiling point of water at lower pressures? So boiling point decreases. So at 1 atmosphere of pressure, the boiling point is 100 degrees Celsius. At Mount Everest, which is 0.33 atmospheres, about 71 degrees Celsius. So it's decreased. How does this affect cooking times? Not longer. So you can get the boiling point very quickly. I mean, relatively quickly. It's actually quicker to start boiling water at Mount Everest than it would be on here, because all we have to do is reach a temperature of 71 degrees. However, the food is going to be cooking at 100 degrees Celsius here, but on Mount Everest it would only be cooking at 71 degrees. Because you're cooking at a lower temperature, if you cook at a lower temperature, that means it takes longer to cook. So what is melting? Yes. What's the definition? So solid to liquid. Is it endothermic or exothermic? So energy is leaving. So you're making the liquid colder to turn it into a liquid. Endothermic. You're pumping energy into the solid to make it turn into a liquid. What is freezing? And is this endo or exo? Vaporization. Is this endo or exo? So you have to pump energy into a liquid in order to convert it into a gas. And condensing. In order for the gas to go back into a liquid, you have to steal some energy from it, so the energy has to leave the system. So it's exo. Sublimation. Solid to gas. And is this endo or exo? So you have to pump some energy into the solid to make the gas molecules move fast enough to make the molecules move fast enough to become a gas. And deposition is the opposite. Gas, solid. And it would be the inverse of exo. We're not doing any of these questions. This isn't on the test, so we can skip over those. So label the graph above with solid, liquid, gas, melting or freezing, and vaporization or condensing. So where would the solid phase be? solid. We're with the liquid. It looks like C to F. I think it's weird. I don't know why. And then the gas phase is up here. And would the B to C be melting, freezing? And here would be boiling or vaporization. Vaporizing. At what temperature does the substance begin to melt? Ooh, what are you reading? At what temperature? Negative 15 to negative 17 degrees Celsius. What state of matter is in the section A to B? D to F? And it could be C to F too. B to C? What is happening to the kinetic energy and potential energy in B to C? What's happening to the kinetic energy and potential energy? Are you sure? So what is kinetic energy, or what is temperature? And is the temperature changing? So kinetic and what's happening to kinetic energy? Kinetic energy is doing what? Staying constant. We're not changing the temperature. But we are pumping more heat into it, so that means potential energy is increasing. Another thing we can say is the kinetic energy there is no change, and potential energy is increasing. Our potential energy increases. So during a phase change, temperature stays constant. Temperature is a measure of kinetic energy, more specifically the average kinetic energy. So if the kinetic energy, or if the temperature is not changing, that means it's staying constant or there's no change to kinetic energy. What letter represents the completed phase change between liquid to gas? Between liquid and gas. A liquid to gas is completed right here. So it'd be G. Which sets of letters represent an exothermic process? So where is energy leaving the system? Not really a trick question. Yes. C to B and G to F. We have to think backwards in time. If we were to rewind, there's an interesting thing. Do you know if you drop a glass bottle onto the ground, theoretically, there's nothing in physics that says it can't just reassemble itself and pop back up on the table. There is no physical law that states it's impossible for a broken glass to reassemble itself, the liquid to move back into the glass, and it just pop itself back up on the table. Completely fine. There's only one law that says it's really impossible, and that's the second law of thermodynamics. Second law of thermodynamics is the universe tends to go to disorder or more chaos, meaning that it's more likely for a liquid to spread out on the ground than a liquid to come back together into a single blob. That's the only law in physics that gives us a direction of time. But technically, theoretically, in physics, everything that can occur in forward in time can occur backward in time. We just never see it occur, and we believe in the second law of thermodynamics. Endothermic would be the opposite. This is the correct forward in time, B to C, and F to G. I don't think I have any trick questions like this. I skipped vapor pressure. You don't need to know it. Yeah, we don't need to know vapor pressure. So, I don't know if you know this, but most liquids, there's a small bit of vapor on the surface due to evaporation, and that vapor can be can generate its own pressure around there. The pressure basically, so it's a partial pressure. It's not the full pressure, but the partial pressure of just the water on the surface, or near the surface of a liquid, is at so there's some water that stays at the liquid surface, and we call this the vapor, and we can measure how much there is by measuring how much pressure is just from the water molecules. I decided to skip vapor pressure in this. It's just not really useful. So let me pull up the test and actually look at it. By the way, the code word of the day. So it's going to be a heating curve, a phase change, a phase diagram curve, kind of like we just did. I'll ask you to figure out normal melting.
Students and teachers, for a quick interruption. Students, if you are planning on playing baseball this year, high school baseball, at some point during the day today, it does not have to be right now, just sporadically during the day today, before the day is over, go by and see Coach Nichols if you're playing high school baseball this year.
So I'll ask you to figure out what the gas phase is, what the liquid phase, what the normal melting, normal boiling, triple point, critical point. I ask you to find what is the triple point from the diagram, what letters on a heating curve correspond to solid phase, liquid phase, just what we did here. I'll ask you what is solid to liquid phase. What's that called? What phase transition or phase change is that? Solid to liquid is melting. Um, I'll ask you, is melting endothermic or exothermic? And I will also ask you questions about kinetic energy and potential energy. So, for example, here the temperature is increasing. So here the kinetic energy is increasing because temperature is increasing. Here the potential energy is increasing. Here again temperature is increasing, so kinetic energy is increasing. Here temperature is constant, so only potential energy is increasing. And during this one, kinetic energy. Potential energy isn't being affected during a temperature change. During a phase change, kinetic energy isn't being changed. So only ever one thing is being changed at a time. You're either increasing the kinetic energy and thus increasing temperature, or you're changing its phase and decreasing potential energy. And it can be in reverse too. The last set of thing on the test deal with system and surroundings. So, see. So, system is wherever we're looking at our the focus of our study. The surroundings is everything else. The universe, we don't really need to know about the universe, but the universe is everything. So whatever we're focused on that's changing is called our system. So if we have mixed some chemicals together and react them, everything else would include the glass, the air, the container. So example in this example, or system would include the water and ice. Everything else would be the cup, the air, etc. It depends on what we're referring to. So the system is loose definition. It's the object of our study. Sometimes our study would just be the ice cube itself, in which case the liquid, the heat is going up and warming, the ice is pulling heat from the water into the ice, warming it up. Let's see if I can find a proper definition. So system, so if we have a liquid and we have some ice inside of it, and we're only talking about phase change of the ice, or system would be the ice cube. Our surroundings, we're only focused on the ice cube right now, so because it's changing, we would let our surroundings be the water and the glass, the air. So in this example, how is heat flowing from the system and surroundings? So what happens to the ice when we put it in water? It does what? No. It starts to melt. How is it? Why is it melting? So is when you melt, do you gain energy or lose energy? Is this endothermic or exothermic? Is the ice cube undergoing endothermic or exothermic? Endothermic. So that means endothermic is when energy goes into a system. So that means heat is flowing from the surroundings into the so heat is flowing from the surroundings into the ice cube. It's not that the surroundings are getting colder, it's that the ice cube is warming up. Warm is a loose term because it's not changing temperature, it's gaining heat. That's in the form of potential energy, but heat is flowing from hot to cold. We'll learn more about that when we go back into heat and start working on the math. But we would say that heat is flowing from surroundings, which would be the water, into system, which is the ice cube. And this is endothermic because it's going into the system. And this is also the ice cube is melting. And melting, you should know, is an endothermic phase change. Any questions? Is everyone going to make 100? There's no math on it. You just need to make sure that you know what endo and exothermic is, how to read a phase change. Yeah, something like that. Yes. There's also a surrounding question like this. There's also kinetic energy and potential energy. So temperature is average kinetic energy. If you increase temperature, you are increasing kinetic energy. Potential energy doesn't change. During a phase change, such as melting, heat is being added, but temperature does not change. Hence, kinetic energy does not change, and heat is being added to potential energy. So when you're heating something up, you're adding energy to it. If it's not during a phase change, that energy is going all into kinetic energy. I'll write that. When heating something up, you are adding energy. If it's not a phase change, all the energy goes to kinetic energy. Temperature changes. If it is a phase change, all the energy goes to potential energy. The configuration of the molecule changes. If it's ice, then they're no longer in a crystal form, they're in a liquid form. Any other questions? That's basically our test tomorrow. Should be relatively easy if you study. Make sure you know. I posted all the PowerPoints too on Google Classroom. So know what the solid to liquid melting. It's endothermic because you're pumping energy into it in order to get it to melt. Know how to read a phase change diagram. That's it. There's no questions for today.